discuss about the time dependent and the time independent Schrodinger equation. Now, before we come into this idea of quantum mechanics, let's just talk a bit about the classical mechanics picture. When we talk in classical mechanics and we are going to define a system mathematically, we use certain laws to get the information about that particular system or a moving body. Now, the Newton's law is a very important aspect of classical mechanics, as well as we are using the concept of conservation of energy, conservation of momentum, and so on. In a similar way, when we actually want to define a system in quantum mechanics, and let's say we have already studied about the concept of wave, and we know what is a de Broglie wavelength, which can be written as lambda is equal to h by p. Schrodinger equation plays a very important role to get information about this particular wave. Now, Schrodinger equation was given in the year 1926, and eventually this helped in understanding the atomic and the molecular system in a much better way. And quantum mechanics was very well developed by the year 1940s and 50s, and explained a lot of unknown phenomena which was not being explained by classical mechanics. So if a question is asked on Schrodinger equation, you can definitely start with a definition. It's basically a wave equation. We're going to look into it, which is written in terms of wave function. So when I say wave function, I'm saying that we are writing it down in terms of the wave function psi. And it will basically predict analytically and precisely the probability of events or outcomes. For example, you want to predict what is the energy of a particular wave at a particular energy state. You can predict that. Okay. You can also talk about the position of at a particular time of a wave. So that means that this wave function is in terms of position x and time t. Now we can have Schrodinger equation in two forms. One is the time dependent equation and the other one is the time independent equation. Now before I come into the expression, we can think about it in this way. We basically have an atom or a molecule, and if it doesn't get affected with time, we actually would be using the time independent equation. But there might be situation where we have an atom and molecule and we are allowing some photons to be incident on it. Now imagine if this photon is incident on it for a longer period of time, it gets affected. As a result, with time, the state might change. So in such cases, we can say that it is time dependent. Right? So in time dependent equation, the expression is this, which we are going to derive, and this is the expression for the time independent equation. I'd suggest you can remember just one of them, and the other one you can easily remember. Let's try to understand it here. We have the time independent equation as I h cross del psi by del t is equal to minus h cross square by 2m into del square psi del x square plus v into psi, where psi is the wave function, h is your Planck's constant, I is iota, t is the time, m is the mass, and v is the potential. Now it's a function of position and time, so x will represent the position. Now let's do certain adjustments and try to bring all the terms on one side. So we have this term, we can bring it on this side, this is the first term, and we have this term, let it be there, and we will bring this term on this side, is equal to 0. Now if you concentrate on this particular term, just check out this term. In the time independent expression, this term will actually be represented by E. So if you remember this and do your minor modifications, you easily remember both the time dependent and the independent expression. So you can see this and this term are the same. We have got psi here, we have got psi here, so we can take it out, and which is only a function of position. And in this term place, we are going to write down E, and in this it should be V. So this is E minus V. So that's a good trick to remember both the equations at the same time. Now what we are going to do is we are going to derive the Schrodinger's time dependent and time independent equation. So for deriving the Schrodinger's time dependent equation, we start with the expression for total energy. Now total energy, as you all know, is actually given by the sum of kinetic energy and potential energy. And kinetic energy is written as half mv square. And let's denote potential energy by just V. So we can divide and multiply by m. We can write it down as 1 by 2m into m square v square plus potential energy v. Now mv is nothing but momentum, so we can write it as p square divided by 2m plus v. Now we are talking about a wave and we are representing that wave by the wave function psi. Now you know a wave is basically a periodic function, so it should be represented in terms of sine and cos function, as we know that any periodic function can be represented in terms of sine and cos or both. Now a wave should have certain information, a wave function should have a certain information when we write it down in the form of an equation. For example, we should know its wavelength and frequency. For wavelength, we know we can use the term k, and we know that k is nothing but representing the wave number, and we can write it down as 2 pi by lambda. Another term that we should know is the frequency omega, which is nothing but 2 pi nu. Apart from that, of course, we should know what is its position and the time that we are considering. So if you consider this, we can write down the wave expression as psi is equal to psi naught e to the power iota kx minus omega t. So this particular term will have all the information about the wave. Now what we are going to do is, since this is the total energy and we are representing it by E, and this energy, since we are talking about wave, is associated with the wave, so we are going to multiply with psi on both sides. So let's just do it. So what you can do is we can write it like this: E psi is equal to p square divided by 2m plus v, and we are multiplying both sides by psi. So that's important, and let's just mark this expression as expression 1. Right. Now we are going to modify this expression slightly, and let's see how we can actually modify this. Now please remember the steps that I'm giving, you can write it down in the same sequence, which will help you to write down your answers and remember it better. So let's start with the expression for k. Now we know that k is equal to 2 pi divided by lambda. So let's write it down. K is equal to 2 pi divided by lambda. Or we know that lambda is nothing but the de Broglie wavelength, so we can write it down as 2 pi divided by lambda is equal to h divided by p. Now we can take p on top and we can write it down as p divided by h, and we can bring 2 pi below h, so we can write it down as h by 2 pi. So this can be written as p divided by h cross. So that means in place of k, we can also write it down as p divided by h cross. Let's do certain modifications with omega. So for that, I can start with the expression E is equal to h nu. Okay, or we can write it down as E is equal to h divided by 2 pi into 2 pi nu. Or we can write it down as h by 2 pi is nothing but h cross, and 2 pi nu can be written as omega. So that means omega can be written as E divided by h cross. So these are the two expressions that we are going to use in order to modify this wave function, right? So what you can say is, therefore, this wave function psi can be written as psi naught e to the power I, and in place of k we can write it down as p divided by h cross. So I'll write it down p here. We already have an x minus, in place of omega we can write it down as e divided by h cross. So we can write it down as e into t is already there, and then we can divide the entire term by h cross. So we can write it down in this way. So let's use this wave function to actually look into the later derivation. So it's a time dependent equation, that means this is a function of both position and time. Let's differentiate this expression with respect to time. Now you might think, why we are differentiating? Because our aim is to derive this expression, and here we can see that it is del psi by del t, and this is del square psi by del x square. So if you remember the original expression, you know that you have to derive or differentiate with respect to t once and with respect to the position x twice. So let's just derive it. Okay, so we can say, therefore, del psi by del t is equal to del t of psi naught e to the power iota, it is e or we can write down px minus et by h cross. This entire term is divided by h cross, right? Now let's just try to differentiate this. It's simple, right? We can just take out psi naught common as nothing but not common. It's a constant. We can take it out, right? And I hope all of you remember your differentiation. So it says that if we differentiate, let's say d dx of e to the power kx, it will be e to the power kx into d dt of kx, so that will just give you k. So here also we are going to do the same. Del del t of this e term, I can write down the entire e term on top, so it will be e to the power I, and this would be nothing but px minus et divided by h cross. So that's done into del del t of whatever is the the power, right? The power term we are going to basically use. So let me just rub this off. So we can write it down as is equal to psi naught del, or we can just, I'm not repeating the same thing, so I'll just write it down as del t into I. The constant or the power is ipx minus et divided by h cross. So we have this expression now, and what we are going to do is we are going to modify this. So we can just simplify this expression further. We can write it down as, now you see psi naught e to the power ipx minus et by h cross is nothing but psi, right? This is the expression for psi. Let's just have a look here. This is the expression for psi. So I'm writing down this expression as just psi, and we are going to take the del del t of this. Now here what you can see is this is differentiated with respect to t, not with respect to x. So we can consider this del del t of x to be 0 first term. So if we just differentiate the second term, we can have it as iota is a constant. We can take it out. H cross is a constant. We can again take it out. We are just doing it del del t of minus of et. So that means there will be a minus sign, and del del t of t is 1. E can be taken out, so it will be just e. So I hope you get this. Del del t of px, this term, we are differentiating with respect to t, so this term will become 0. Then we can differentiate the remaining terms. So this way what we are going to get is this, right? So one more thing, that, or maybe write it in a simpler way. So this is done. We can divide the numerator and denominator by I. So we can just simply write it down as I divided by I. And then what we can do is, final expression would be del psi by del t is equal to, now I into I is I square, and I square is minus 1, and minus minus becomes plus. So this will just remain as psi, and on top it will remain just e, and in the denominator it's an I, so I will write it down as e divided by h cross as the term, and then this can be written as 1 divided by I. So this is the expression for del psi and del t. And what we can do here is we can just further simplify this. I h cross can cross multiply here, so I can write it down as I h cross del psi del t is equal to e into psi. And this is an important term. So this is the derivation that we needed for in terms of del psi del t. Let me just keep it inside the box and mark it as number 2. Next, if you look into the previous expression, we want to find out del square psi del x square. So let's just do it now. We are going to double differentiate the term with respect to x. So let's try doing this. So what we can do is, now del psi del x is equal to psi naught is a constant. I can take it out, and then again the same way of differentiation, I can take e to the power I p x minus e t by h cross, and now we are differentiating it with respect to x, so I can write it down as del x of the term, right? We're having psi, so we already know what's the form of psi. So del x of I, the differentiation pattern is something similar, et divided by h cross, right? So again we know this entire term is psi, this entire term is psi, so we can write it down as psi, and for this, now it is with respect to x and not with respect to t, so this term is 0, so we just have the term as I is there divided by h cross, and then del x of px will just give you p. So this is the term that we have, right? In a similar way, we can do the double differentiation. In double differentiation, what does it mean? It means that we are going to differentiate. I can write it down as del x, okay, of del psi del x. So del psi del x is this. So we can just write it down as del x of psi I by h cross into p. So we can just write down it. We can take out I by h cross outside. We can take p outside. That's the momentum, and we can have del psi del x. Now del psi del x is already derived here, so we can actually use this expression directly. So that means I can write it down as I by h cross into p, and del psi del x is nothing but psi into I by h cross into p, right? So that means this can be written as I into I is I square, so I can write it down as minus p into p will become p square, and h cross into h cross will become h cross square, and then we can just simply write down it as psi. So that's the expression for del square psi del x square, and let's take this expression as expression 3. So this is our expression 3. Now we have 3 expressions, 1, 2 and 3, and what we can do is we can replace 2 and 3 in 1. Now let's just have a look back in expression 1. Where was the expression? This was our first expression where we multiplied the total energy with psi on both sides. So here we have got psi. So let's just try doing it. So if we replace it, okay, let's write down the entire expression again. We have our expression 1 as p psi is equal to p square by 2m plus v into psi, and what you can see here is E psi, and this is our E psi. So this is I h cross del psi del t. So let's just replace this here. So what you can do is, therefore, putting 2 and 3 in 1. So this is our first expression. So what you can see is E psi in place of E psi, okay, we can write it down as I h cross del psi by del t, as you can see. So we can write it down as I h cross del psi by del t is equal to, now look into this term, let's just open the bracket. It is 1 by 2 pi 2m, it is 1 by 2m, okay, into p square psi plus v psi, right? So this is 1 by 2m p square psi by v psi into v psi. So what we can do now is we can just replace p square psi, okay, and from here I think you can get it, right? If you just look into this expression, you can see that p square psi is equal to minus of, we can cross multiply, so this would be h cross square into del square psi del x square. So we can replace it here, so we can say it is I h cross del psi by del t is equal to minus of h cross square by 2m into del square psi del x square. So p square psi we are replacing with this plus p psi. Okay. So there are different ways of writing down this expression. If you keep it like this, no harm. Okay, that will actually represent the Schrodinger's time dependent equation. But you can see I have written it in this form. So this is the form that you can also keep it. So this is the expression, and this is what we are deriving in the Schrodinger's time independent expression. A good way, to remember this is to just looking into it once or twice a day, okay, before your exams, and then you can remember the time independent equation when you know this. It's very easy. Okay, so it's important to remember because you'll be doing a lot of derivations based on this single harmonic potential well. Okay, infinite potential well. If it is time dependent, we can derive it using this expression. Now, what we want is we are going to derive the Schrodinger's time independent expression. That means we are going to get rid of this t term. Okay, so when we are talking about the time independent term, it means that psi is a function of x and t, and when we are writing down the time independent term, psi will remain as a function of x. Of course, t would be there, but it won't affect the wave function that we have. So this is something which we are going to do in the next lecture.